In today's video, I'll be discussing the limitations of the marine radar. This is video 4 in the series of videos I am making on this topic. I have given the links to the previous videos in the description section below. So make sure that you watch all the videos to understand how the radar works and its limitations. So generally speaking, there are three factors that govern the display of a target's echo. If you don't know, a marine radar is used on ships to detect targets, that is other vessels or landmarks or buoys, and also it is used for collision avoidance or position plotting at sea. So these three factors that govern the display of a target's echo are the functioning of the radar equipment itself, external propagating conditions, and the nature and composition of. So far, in my previous videos, we've looked at the radar and its components as well as their functions. So I thought the next obvious step will be to look at the propagation conditions, that is the environment, and its effect on the detection of a target and the subsequent display of the target's echo. Sometimes these external factors can either aid or disadvantage the detection and display of targets and their echoes. Where there is a downgrading of the target response, there is considered to be a limitation imposed on the functioning of the radar. So I'll start with the radar horizon here. Because of the curvature of the Earth, there is a definite limit to how far we can see with the naked eye. This is called the horizon, and we also know that its distance from us will depend on how high we are. The higher we are, of course, the further we can. If you look at the figure, there are three horizons represented. The nearest to the antenna, which is T, is the theoretical horizon, as it is a straight line touching the Earth's curvature. That is as far as we ought to be able to see with the height of our eye equal to the scanner height. However, light does not travel in straight lines. It is bent or refracted by whatever medium it is passing through. Just as a stick appears to bend when you poke it into a pool of water, light is also bent passing through the Earth's atmosphere. The result is that light waves are bent around the curvature of the Earth, which allows you to see slightly further by about say 6 to 7%. This is known as visible horizon, or the letter V in the diagram. Radar waves, which are at microwave length, are also refracted like light because they are at a lower frequency. They are bent even further around the Earth's curvature. The radar horizon R is consequently even further away, and theoretically it's 15% extra. It is possible, with the knowledge of the definite radar horizon, to calculate how far away we can expect to see various objects on the radar. The radar horizon is given by the simple formula that range in nautical miles equals 2.2 under root of the h, where h is the height of scanner in meters, plus 2.2 multiplied by a small h, which is equal to height of object in meters. The formula is for standard meteorological conditions. Temperature, air pressure, and humidity can cause the amount of refraction of a radar wave to vary. If you have noticed in the previous figure, if the scanner is on an island with a height of 150 meters and the height of fishing vessel is 4 meters, then the extreme range at which you can expect to see the fishing vessel on the radar is about 31.34 nautical miles. That is putting the application or putting the formula in application. The theoretical relationship for the formula to be correct assumes standard atmospheric conditions are prevailing, radar pulses are sufficiently powerful, target will return detectable echoes, and weather conditions such as rain will not attenuate the signals. Standard conditions can be defined as a temperature altitude of 15 degrees Celsius, which is decreasing 2 degrees Celsius every 1000 feet of altitude. Air pressure is 1013 hectopascals, decreasing 36 hectopascals every 1000 feet of altitude, and humidity 60% constant with height. Where non-standard conditions prevail, then it is possible the radar horizon is either decreased or increased. Non-standard conditions are known as super or sub-refraction conditions, which I will explain. So earlier it was seen that the Earth's atmosphere refracts the radar beam to produce a radar horizon which is longer than the visual horizon. As weather conditions can affect the atmosphere, it follows that this will also affect the radar horizon. So in this we talk about super-refraction and sub-refraction. Now in super-refraction causes an effective increase in the radar horizon. Radar beam is bent downwards more and targets are detected at ranges greater than normal. 40% increase in target detection is not uncommon. Atmospheric conditions normally associated with super-refraction include a decrease in relative humidity with height, temperature falling more slowly with height than standard, as well as fine settled weather and high pressure systems, warm air flowing over a cooler sea. Ducting or extra super refraction. Here the radar pulse is trapped in a duct which is formed by the Earth's surface and highly reflective layer in the atmosphere. It is a concentrated energy which is otherwise lost into space. The pulse follows the Earth's surface and extends dramatically the radar horizon. Atmospheric conditions normally associated with ducting include highly reflective layer required, that is pronounced temperature inversion where temperature actually increases with height, not decreases with height, and pronounced decrease in relative humidity with height. It must be remembered that super-refraction causes an increase in the detection range of targets, not an increase in range accuracy. Ducting can cause the presence of a particular false echo on the display, the second trace. This is the thermal inversion where the temperature increases with height rather than the usual decreasing of temperature with height. To sub-refraction, which is an effective decrease in the radar horizon. Here the radar beam is bent downwards less than normal, where the 20% decrease in detection range is not uncommon. The atmospheric conditions associated with sub-refraction include an increase in relative humidity with height, temperature falling more rapidly with height than standard, and associated with bad weather and low pressure systems, where cold air is flowing over a relatively warmer sea. This is the diagram showing you the sub-refraction where colder air is aloft. Temperature is falling more rapidly with height. In the other, the super-refraction, we had temperature increasing with height. We had the concept of temperature in. So here we have the formula for the normal propagation, and then this is just a summary of what we've talked about so far. I'll move on. I'll talk about the weather effects and clutter. So just as heavy rain and similar weather conditions can affect visual detection of objects, weather will also have an effect on the radar picture. The most persistent problem is from the clutter. Let's talk about sea clutter first. So in absolutely flat calm sea conditions, the sea surface will act as a mirror and all the radar energy which strikes it will tend to be reflected away from the antenna. As wind speed increases, wavelets and waves form and their height will increase in proportion to wind speed, and as waves form, a mass of unwanted echoes will extend around the antenna position. Sloping wave fronts near the antenna present a more favorable aspect for the reflection of the radar energy than those at a distance. As the range from the antenna increases, the aspect of the wavefront becomes more unfavorable rather, until the direction of the pulse will become tangential to the top of the wave. In such a case, the radar pulse will graze the top of the wave and clutter echoes will not be detected beyond this range. The extent of sea clutter echoes will depend on the following factors. Wind speed and direction. The clutter will increase in strength and range as wave height increases. The windward side will provide steeper waves, hence clutter will extend greater to windward. In certain conditions, it is possible to recognize the line of approaching wave fronts where a long swell is present. The antenna height, the higher the antenna, the further out the clutter will extend. Radar wavelength, the roughness of the wavefront will be greater for 3 cm than for 10 cm. As a consequence of this and other effects, the 10 cm wavelength will show less clutter echoes than the 3 cm. And finally, the radar pulse length, where selection of long pulse will increase the number of C clutter echoes on the screen. Selection of short pulse will reduce the C clutter response near the antenna location, but it will also reduce the response of wanted targets or tracks over the entire screen. Then we move on to the sensitivity time control or STC. Now remember, targets with a stronger echo strength than the clutter which is not saturating the display. Such targets are capable of detection but are not obvious against the background of the clutter. Here, use of the STC control may assist identification. So targets with stronger echo strength than the clutter which is saturating the display, this may occur with the 3 cm radar with very strong C clutter echoes associated with stormy weather. Such targets are still capable of detection using the STC control. The STC control or swept gain is a suppression control which affects the amplification of echoes out to a certain distance from the antenna location. It does not affect the entire screen, which is good, as the C clutter return is only clustered around the area of the antenna. STC controls can be manual or automatic, and sometimes they both may have to be used, but mainly manual is used. Any manual STC control must be used carefully, as too much suppression gets rid of not only the C clutter echoes but also the echoes that you want, the wanted echoes. Remember, this control affects all echoes with a certain set distance of the antenna. Ideally, the operator wants to optimize suppression to match the clutter response, thus leaving wanted targets painted against a light residual clutter. Also, the weather conditions change the amount of suppression must be varied to compensate. Thus, no single correct manual setting for the control. The operator must periodically and systematically search with the control to obtain optimum suppression. This is not an easy task for an experienced operator, however, it must be considered. Test targets within the STC control area should be regularly checked. Now I'll talk about the scan-to-scan correlation. This is available with most raster scan displays. The STC control uses difference in echo strength to search for targets in an area of clutter. An observer can identify a target by the irregularity of its response compared to the random C clutter returns. Scan-to-scan correlation does this task automatically by comparing the contents of two range cells or to two or more successive antenna rotations. The probability that a wave will occupy the same range cell for two successive rotations is less than that of a target. By using 3 scans, the probability is increased again. But craft with high speed may quickly change cells and hence not be detected. What I meant by cells is displayed here on your screen. Correlation techniques will reduce the C clutter response, but it may eliminate high speed targets. Scan correlation can also be used to show an artificial afterglow showing the past position of targets. The afterglow trail is shown in sometimes different colors to the radar echo. And in some cases of radar, an indication of the target's relative motion, if it is in relative motion, or the target's true motion, if in true motion, is displayed as well. In terms of precipitation clutter, precipitation is the aggregation of a large number of randomly distributed individual water particles. It causes two effects on the radar picture. Firstly, unwanted echoes on the PPI, which can mask out targets, and attenuation or weakening of the particle size must be considered in relation to transmitted wavelength. Radar response is proportional to the square of a particle diameter. Hence, a doubling of particle size will produce a four-fold increase in radar response. Radar response for a given particle size is inversely proportional to the square of the transmitted wavelength. Hence, under given precipitation conditions, a S-band or a 10 centimeter radar will reduce the rain clutter responses to 0.1 of that experienced by a X-band or a 3 centimeter radar. Rain clutter responses increases in proportional to rainfall rate. The different types of precipitation are rain, where most echoes and most attenuation of all the types that affect particularly heavy tropical rain. We have the snow and sleet. We have the hail, fog, clouds, as well as sand, dust and smoke. Sand, dust and smoke normally have no effect on the radar. A difficult problem, particularly with X-band radar, is suppression of rain clutter. S-band radar will show fewer echoes from precipitation and also suffer less attenuation. There are techniques to aid target detection using the pulse length. So change to short pulse to reduce precipitation echoes. Go to long pulse to search for targets beyond the rain. In terms of the sensitivity time control or STC control rather, it is only effective if rain is in the area of the antenna and if searching for targets in precipitation. The rain clutter control is used for searching for targets in rain showers and not effective in heavy rain. Finally, we talk about radar for navigation. The radar greatly enhances our capabilities to navigate safely in darkness and restricted visibility. In daylight and clear visibility, radar also provides the advantage of accurate range measurement and perspective. Position fixing at frequent intervals is essential, firstly to monitor the vessel's progress along the planned route and also to keep records for operational purposes. The radar is particularly good at measuring ranges accurately. Due to limitations of the radar, bearings observed on radar are generally not as accurate as radar ranges. Thus, wherever possible, we try to use radar ranges for position fixing as a preference over radar bearings. Position fixing with landfall. So before making landfall, radar in thick weather or darkness, study the meteorological conditions to see whether anomalous propagation is likely. Study the chart for any target which may have good echoing characteristics and is likely to prove a good target at long range. Although without previous radar experience of the locality, this may be difficult. A table or graph of distance to radar horizon for standard conditions will provide a useful guide to possible detection ranges for the targets available. Radar position fixing at long ranges. It is highly unlikely that positive land identification is made by range and bearing of a single echo unless it is recognizable from past radar experience in that locality. A position obtained from less than 3 positively identified long-range echoes should not be accepted with any confidence. These can be plotted using tracing paper as a station pointer fix. The value of previous knowledge of the appearance of echoes obtained in clear weather is invaluable. Remember that the strongest echo is not necessarily the highest mountain, nor need the first echo seen necessarily be the highest object above the radar horizon. At a greater distance, the need for accuracy is not so acute as when closer in, but the sooner an accurate fix is obtained, the better. Echo sounders may assist, so may a GPS or Lorenzi. If the identity of a single echo is positively known, single bearing and range will give us reasonable approximation of the ship's position at long range, providing all circumstances are borne in mind. For instance, second trace echoes are not usually of much use unless they are from an isolated target such as an island, when they might give a rough position. In any circumstances, it is always good seaman-like practice to treat the first radar position with some caution and to check the position frequently as more targets. Having obtained perhaps a reasonable fix by long-range method, the ship approaches to a distance from the coast where other radar fixing methods are available. The need for accuracy increases as the coast is neared. Depending on the topography, the coastline features should become positively recognizable at a range from 15 miles downwards and seldom less than 8 miles in practice. It should be emphasized here that no matter how simple and direct the radar evidence should be, it is highly dangerous to neglect keeping a proper reckoning and estimated position, and to fail to check any drift from fixes obtained. For important fixes, it is best that the navigator himself should read off the ranges and bearings from the PPI, and the efficiency of individual observers at the interpretation of the display varies. Methods of fixing by radar. It has been explained that range accuracy of radar is high, where its bearing accuracy is low compared with that of a visual observation. The descending order of accuracy of radar or radar-assisted position fixes may therefore be stated as radar ranges and visual bearing of prominent isolated objects, radar ranges of several radar conspicuous objects plotted as position circles, and then radar range and radar bearing of a single charted feature. So if possible, try to start from the radar range and visual bearing, then use the radar ranges of several objects, and then only use radar range and radar bearing. It is here assumed that the range of a prominent isolated object can be more accurately measured than those of merely radar objects. The main consideration in relating radar range to the chart is the determination of the point of land which corresponds to the nearest edge of the echo on the radar screen. The first choice should be which is high and steep too, in the direction of the observer, failing that the amount of possible error must be estimated and allowed for. Whenever possible, a check range of another object is advisable. This method is also useful when weather is thick enough to obscure all but closest objects, also in clear weather when visual cross bearings are unobtainable. Example, when passing an isolated land or lighthouse. In terms of position fixing by radar, we have the radar ranges for clearing lines and parallel indexing techniques, which we will discuss more in my next video. So I'll stop the video here now because it will become unnecessarily long. In my next video, I'll talk about the parallel indexing techniques as used by the radar and what are the factors that affect it. Thanks guys. Bye for now.